Hi everyone. So today we're going to look at the new section under polar coordinates, and that is conic sections. Okay, so conic sections is about unifying the parabola, the ellipse, and the hyperbola into one group of shapes, okay, that are all described by a similar equation, okay, and that's going to be the conic section equation. Now, you can write this equation in Cartesian form, and you may have seen that before, but now we are going to write it in polar form since we're going to be looking at this in terms of polar coordinates. Okay, so first we're going to look at a new definition for parabolas, ellipses, and hyperbolas, and then we're going to see how this definition relates to this polar form equation. Okay, so firstly, we're going to look at the parabola. Okay, so we're all familiar with the Cartesian form, y equals x squared, or something similar to that. But here we're going to define the parabola a bit more geometrically. Okay, so what we do is we pick a point, F, okay, we call that the focus, and we draw a line, L, called the directrix. Okay, so this line L, that's called the directrix. So F, that is for focus, and L, that is called the directrix. Okay, and using these two things, we can then define the parabola. Okay, so the parabola is the set of all points, these points here, such that the distance from F to the parabola, so let's say it stops at this point P, and then down to the directrix, the ratio between this first distance FP and the second difference PL, that ratio is a constant. Okay, and in fact, the special case for a parabola, these distances are the same. Okay, so the ratio, which we call the eccentricity, or E, is given by the distance FP over PL. Okay, we call that the eccentricity, and that just defines the shape. So different values of the eccentricity will give us different shapes. So in this case, when these distances are the same, we get an eccentricity of 1, which means we are dealing with a parabola. Okay, in other situations, like with the ellipse and hyperbola, we're going to get a different eccentricity value, and that will give us the different shape. Okay, so that's how we define the eccentricity. So E is eccentricity. Okay, so that's for the parabola. Let's look at the ellipse. Okay, so it's defined very similarly. So we've got a directrix line. For this case, let's do it vertical, okay, just for something different. So we've got a vertical directrix line. We've got a focus. Okay, similar to what we had before. But for the ellipse, we have 2 focus points. Okay, we got another focus point here. So let's say that's F1 and that's F2. Okay, then again, we've got the ellipse shape, something like that. And again, we can define it in terms of this eccentricity value. So we pick a point on the perimeter like that. So this distance divided by this distance here, that's going to give us our eccentricity value. Okay, so the distance from the focus to the circumference or the perimeter, and then from the circumference or perimeter to our directrix line, that ratio gives us the eccentricity, which is a constant for all points P going around the ellipse. Yeah, so that's how we determine these points. Okay, so all the points that satisfy that condition forms part of the ellipse. Okay, and the third one is the hyperbola. And again, we define it in a very similar way. We've got a focus. And similar to the ellipse, we've got two focus points. So we've got, let's say, F1 here, and then F2 here. Okay, we've got our directrix line, L. Again, very similar thing. We've got the hyperbola, comes through like that. And like that, maybe you've seen that before. Okay, and then we've got the same sort of condition. So we've got this distance from the focus point to the curve. So that distance from F1 to P, divided by this distance from P down to the directrix line. Okay, the ratio of those distances, again, we call that the eccentricity, and that is a constant for this hyperbola. Okay, so if you pick any point P along the hyperbola, you're going to calculate the same eccentricity value. Okay, and that's the eccentricity value that defines this the shape of this hyperbola. Okay. So just a note on these eccentricity values. So eccentricity E and conic and categorizing or classifying conic sections. Okay, classifying conic sections. Okay, so like I said, this value of E you can calculate, and that determines the shape of the curve that you're investigating. Okay, so if E is less than 1, so that's case 1 here. So if E is less than 1, then we call the shape an ellipse. Okay, number 2, if E is equal to 1, so that's what we had in this first case, where those two distances are the same. So if E is equal to 1, then we call the shape a parabola. And number 3, if E is greater than 1, okay, then we call the shape a hyperbola. Okay, so if it's less than 1, it's an ellipse. If it's equal to 1, it's a parabola. If it's greater than 1, we call it a hyperbola. Okay, so that's how we classify the different conic sections based on their eccentricity values. Okay. Now, like I said, this idea of conic sections is to unify these 3 different shapes into one group that we call conic sections. And together with this, we have the so-called conic section equation. Okay, so it's one equation or one form of an equation that describes all 3 of these shapes. Okay, so the conic section equation in polar form, that's what we're going to look at it. In polar form, is technically 2 equations, but we'll see that we can relate them. So the conic section equations in polar form are 2 equations that describe parabolas, ellipses, and hyperbolas. Okay, so it's like one equation, or in this case, two equations that describe all three. Okay, so what do these equations look like? Okay, so the first one, r of theta is equal to e times d over 1 plus or minus e cos theta. Okay, so we'll see what this value of d is, and this plus or minus just depends on where the directrix line is. Okay, so we'll see how to pick those values there. Okay, so that's for cos, and we'll see in which cases we use cos. And then the other one, r of theta is equal to e times d over 1 plus or minus sine theta. And we'll look at in which cases we use sine theta. E sine theta. Okay, so it's the eccentricity times sine theta. Okay, so we're just going to look at the cases with a parabola, but the same thing applies for ellipses and hyperbolas. Okay, so let's just sketch the following. So we have x and y. Okay, so I'm just putting the Cartesian coordinates here, Cartesian axes, so that we can determine distances. We can measure distances using distance formula or something like that. Okay, so for the first case, we're going to look at what happens when the directrix is over here. Okay, that's L, the directrix, and then our focus is at the origin. Now, if the focus is not at the origin, then we can always just shift our coordinate system so that it is at the origin. Okay, so that's not too much of a problem. Okay, and then we've got our parabola, something like that. Okay, so in this case, we see that this directrix line is given by x equals d. Okay, so that's the d that appears in this equation here. So x equals d. Okay, so we have a positive value of x for the directrix line. So in that case, we use the following form of these equations. So we have r of theta is equal to e times d over 1 plus e cos theta. And an easy way to remember that is that the directrix line is given by x equals something positive. So the x, remember for polar coordinates, x relates to cos. So that's why we use cos. It's a positive value, so we use plus e cos theta. Okay, so that's case 1. For case 2, what happens if the directrix is on the other side? So we have a similar situation. We've got our axes here, x and y. The focus, again, that's at the origin. But now the directrix is on the other side. That's L. This is now something like x is equal to minus d. Okay, so in this case, our parabola is going to look something like this. And I'm sure you can guess which form of the equation we use. It's going to be something like r of theta is equal to e times d over 1 minus e cos theta. Okay, so we choose cos theta because the directrix is given by x equals something. Okay, x goes with cos. We have a negative value of the directrix, so minus d, because it's on the left there. So we have minus e cos theta. Okay, so everything makes sense there. Okay, so these are for vertical directrix lines. We can also have a similar thing with horizontal directrix lines. Okay, so again, we draw our xy axes. Okay, and let's say we've got a horizontal directrix line here, y equals d. Again, the focus is at the origin. If it's not at the origin, we can just shift it so that it is there. And then we've got our parabola, something like that. Okay, and for this one, very similar to what we had before, r of theta is going to be E times D over 1 plus, okay, because the directrix line is above the x-axis, but now we're using y equals D, so it's going to be plus E sine theta. Okay, something like that. And I'm sure you can guess the last case. That is when the directrix line is horizontal, but below the x-axis. Okay, so we have something like this. X and Y. Okay, we've got the focus over here again. Directrix line over here. So this is at y equals minus D. And we can draw in our parabola like that. Sorry, that's something like that there. Okay, so for this case, we're going to have something like r of theta equals E times D over 1 minus E sine theta. Okay, so again, we're using a horizontal directrix line. So we have y equals something, so we use sine. That something is negative, so y equals minus D. So we use 1 minus E sine theta. Okay, so very easy to remember. Okay, so let's look at an example and then, an example of finding the equation, and then I'll leave the sketching as a homework exercise. Okay, so example. Okay, so find a polar equation for a parabola that has its focus at the origin okay, and the directrix is given by y equals minus 6. Okay, so we know that it's a parabola, so that tells us that E is equal to 1. Okay, because of the eccentricity of a parabola is always 1. So E equals 1. And the directrix line is given by y equals minus 6. So that means D is equal to 6. Okay, so that distance to the directrix is 6 units. Okay, so what kind of shape are we dealing with? Well, the directrix is below the x-axis. It's y equals minus 6. And it's a horizontal directrix. So that means we are dealing with this case over here, okay, this last one, where y equals minus something. So it's going to have this form here. E times D over 1 minus E sine theta. D is going to be 6. E is going to be 1. So this gives us r of theta is equal to 6 over 1 minus sine theta. Okay. And then I'm just going to leave it as a homework exercise to try and sketch this. Okay, to see what kind of parabolic shape you get. Okay, so sketch this conic section. Okay, so that's example 1. Okay, example 2. Okay, so a conic section is given by r of theta is equal to 10 over 3 minus 2 cos theta. Okay, something like that. Okay, so it doesn't look exactly like what we had before, but remember, we can always manipulate the equation so that it looks like this over here. Okay, or one of these four. We can always manipulate it to look like that. Okay, so a conic section is given by this polar form. And then we need to find, number one, the eccentricity. Number two, the directrix. Okay, and then after that, we need to sketch it, but I'm going to leave that as a homework problem. Okay, so this is not exactly what we had before, because remember it was E times D over 1 plus or minus E cos theta. Here we got this 3. Okay, we want to get rid of that. So what we can do is divide top and bottom by 3. So R of theta is equal to 10 over 3 minus 2 cos theta. Okay, that's what we start off with. We can divide top and bottom by 3. So we have 10 over 3 divided by 1 minus 2/3 cos theta. Okay, so now we've got the 1 minus E cos theta in the bottom. But remember, in the top, it's E times D. So this top factor is E times D. Okay, but we know E is 2/3, so we can calculate D. So D is equal to 10 over 3. Okay, but divided by E. Okay, just dividing both sides by E. So that's going to be 10 over 3 divided by 2 over 3, which we identify from this bottom factor here. That's E. And this is equal to 5. Okay, so that is our distance to the directrix. Okay, so the eccentricity was 2/3. Okay, and then the directrix D, the distance there was 5. Okay, but we can see that this is cos theta. So we know that we are dealing with a vertical directrix, so it's going to be x equals something. We also have that it's minus E cos theta. So we're going to have x equals minus 5 for the directrix line. Okay, so that's the equation of the directrix. Okay, so D equals 5, that's just the distance to the directrix. X equals minus 5, that's the actual equation of the directrix. Okay. Okay, so that's the first part, and then the second part I'm going to leave for homework is identifying what kind of conic section this is and then sketching it. Okay, so number 2, that's going to be homework. Identify the conic section or the type of conic section. Let's identify the type of conic section and sketch it. Okay. Okay, so that's going to be everything for today. So tomorrow we're going to go through more on this equation here. So finding the equation, giving some information, and sketching the resulting curve. Okay, if you do have any questions about what we've gone over here, please just ask on the WhatsApp group, or you can send me an email. And remember that the tutors are also on the WhatsApp group, so you can ask them as well. Okay, so tomorrow we will carry on with this sketching and finding the equation.